Good evening, everyone, and welcome to my presentation entitled on Analysis of Boundary Layer Flow over a Moving Plate in a Porous Media. Myself, Suman Sarkar, a senior research scholar at the Department of Mathematics, National Institute of Technology, Rourkela, India. The outline of my presentation will be following. Let's begin with introduction. And first of all, we will discuss about boundary.
Professor Sarkar, we cannot hear you.
Yes, ma'am. May I audible now?
Sorry, we can hardly hear you.
Sorry, ma'am. There is some problem. May I audible now?
Sorry, we can hardly hear you. Please raise your voice.
Everything is. Can you hear me, ma'am? Now?
Yes, we hardly hear you.
Can you hear me, ma'am?
It's perfect.
May I audible now?
Yes. Please, you can start in the first slide.
Ma'am, may I audible now? Hello?
Hello, we can hear you. Yes, please go on.
Okay. Let's begin with introduction. And first of all, we will talk about a brief of boundary layer problem, and then we discuss our main problem. After that, via literature survey, a few questions will arise, and that develops our research objectives and goals. First question arises in mind: what is boundary layer? A boundary layer refers to the layer of a fluid in the immediate vicinity of a bounding surface where the viscosity are significant. In fluid practical engineering, one of the biggest breakthrough is concept of boundary layer, and it was demonstrated by Ludwig Prandtl in 1904. Some examples of boundary layer are the atmospheric boundary layer is within 1 kilometer from the surface, and human boundary layer around human's body surface is given in picture. And in this, after Prandtl boundary layer theory, a numerous applications for boundary layer theory has been described by numerous researchers. In this problem, we consider viscous fluid flow past a rough plate through a porous medium. We consider a plate velocity is UW and free stream velocity is U infinity. According to the velocities, two types of boundary layer arise, and the schematic diagram of the boundary layer flow domain is given in figure A and figure B. And this type of moving plate problem first examined by Blasius, a former student of Prandtl. He considered the problem of fluid flow along a stationary plate. In contrast with Blasius, Sakiadis considered the fluid flow over a moving plate in a quinset fluid. Due to its industrial and practical applications in modern engineering applications such as metal and polymer extrusion, crystal growing, and many others. This type of problem has been extended by various researchers by adding various physical phenomena such as magnetic field, porous media, non-Newtonian fluid behavior. Cortell combined both Blasius and Sakiadis problem by considering boundary layer flow for free stream passed along a moving plate. Fang et al. Consider the effects of slip boundary conditions over a moving plate. Bhattacharya et al. Describe the effects of slip flow over a stationary plate when the plate is embedded in a porous media. It is noticed that the governing equations with viscosity are known as Navier-Stokes equation, which are nonlinear coupled elliptic equations. This nonlinear partial differential equation can be reduced into a ordinary differential equation by choosing a suitable similarity variables. To understand the flow behavior, the reduced differential equations are solved numerically in absence of analytic solutions. And from numerical solutions, other researchers conjecture regarding this existence and uniqueness behavior of the solutions, and one can verify it mathematically. There are many general tools to verify this existence, uniqueness, analytic behavior, and Poulet, using topological shooting method, demonstrated the existence and uniqueness results in his paper. By above literature survey, our aim is to carry existence and uniqueness results of the resulting governing boundary problem along with numerical solutions. So we first consider a boundary value problem. Our main objective, first consider a boundary value problem, then we reduce the governing Navier-Stokes equation into nonlinear OD, then we discuss the analytical results, the existence and numerical results of the reduced differential equation. Next, numerical results, and discuss mathematical formulation. The mass and momentum conservation equations are given in equation 1 and 2. And the boundary condition at the wall is U equal to UW plus lambda star del U del Y. Here lambda star is for slip parameter. When lambda star equal to 0, the velocity at the wall is equal to plate velocity. Our UW is plate velocity, and far from wall, our velocity is equal to free stream velocity, that is U infinity, when our y tends to infinity. In this case, we consider the similarity variable in this form, where U is the summation of plate velocity and free stream velocity, and f zeta is one of the dimensionless stream function. Substituting 1, 2, 3, 4, substituting 5 in 1, 2, 3, 4, the governing equation 1, 2 reduces into equation 6, and the boundary condition 3, 4 reducing in 4, 5. So our aim is to discuss the existence and infinite results for the governing equation 6 with boundary condition 7 and 8. Here the governing parameters are gamma, and gamma is the ratio of U infinity by U, and U is the summation of U omega plus U infinity, and therefore clearly our gamma lies between 0 to 1, and our this omega is related to our porous medium, and it is always greater or equal to 0, and lambda is related to our slip parameter, and lambda is greater or equal to 0. So our aim for these governing parameter values, we want to prove the existence and uniform results of the solutions. To prove the existence results, we need to prove the following theorems. For any omega greater than 0 and gamma lies between 0 to 1 and lambda greater than 0, there exists at least a solution to the boundary value problem. And further, we also prove that the solution's first derivative is monotonic, and it is also decreasing if our gamma is less than 0.5 and increasing if gamma is greater than 0.5. We use topological shooting argument to prove the existence results. In topological shooting argument, we first transform our boundary value problem into initial value problem by considering f double dash 0 equal to alpha, and this is our initial condition, where alpha is free variable. We can choose from anything, a real value. For any real value, there is a solution of initial value problem. Our governing equation 6 and this equation 9 has a solutions, and the solution is depend on and alpha also. Hence, the solution of initial value problem, IVP initial value problem, are denoted as f zeta alpha. And our aim, therefore, not all alpha will satisfy the boundary condition at infinity, that is f dash infinity equal to gamma. So our aim is to find at least one alpha star such that f dash infinity at infinity alpha star tends to gamma. This is our aim, is to find one alpha star, and this proof is divided into two cases when gamma is lies between 0 to 0.5 and another case is 0.5 to 1. It is worth mentioning that the boundary value problem has a exact solutions at gamma equal to 0.5. Gamma equal to 0.5 means our free stream velocity and plate velocity are equal, and that time the exact solution will be f zeta equal to 0.5 zeta. And for this case, we first assume our solution's first derivative lies in gamma to 1, and in topological shooting argument we need to choose shooting domain. The parameter alpha is called shooting parameter, and we choose the shooting domain is minus infinity to 0, and considering two set x1 x2 in such a way such that solution does not lie into the set. And in this case we choose s1 is a collection of alpha such that f double dash corresponding solutions, so second derivative f double dash become 0 whenever or f dash greater than gamma, and in s2 is a collection of alpha such that f dash become gamma whenever f double dash greater than alpha less than 0. And using lemma 1, lemma 2, lemma 3, we basically prove that S1, S2 are both non-empty, open and disjoint set, and it is a subset of minus infinity to 0, and the minus infinity 0 is a connected set. So we cannot, S1 union S2 is a disconnected set using definition of disconnectedness. So S1 union S2 not equal to minus infinity to 0 is a symmetric diagram. Hence there exists a alpha star which lies between minus infinity to 0, which neither alpha star neither in S1 nor in S2. Therefore the corresponding solutions of alpha star will satisfy the properties f dash greater than gamma and our f double dash always less than 0 for any zeta greater than 0. Hence from our main equation it is easily proved that our f dash tends to gamma. This gives existing results for our boundary problem for this case. Now in second case it is also similar. In similar way we can prove by considering these two set S3 S4, and using a similar argument we can prove the results, existing results for the gamma when gamma is lie between 0.5 to 1. Now for uniqueness results, the following theorems will be proved. The theorem statement is the for any omega greater than 0 and gamma is lie between 0 to 1 and lambda less than 0, the solution of the boundary problem is unique. Unique means there exists only one alpha. We suppose if not, we suppose there exists two alpha. One is alpha 1 and alpha 2, and the corresponding solution will be denoted as f1 and f2. And we satisfy all the previous boundary conditions with f1 double dash 0 equal to alpha 1 and f2 double dash 0 equal to alpha 2. This argument also partition into two cases, when gamma is less than 0.5 and when gamma is greater than 0.5. Now this is the outline of the proof. We in some consideration there is a contradiction, we get a contradiction, and the contradiction is for that we consider there exists two alpha 1 alpha 2, but we have a contradiction, hence there exists only one alpha. And in similar argument for this case also we get a contradiction, and hence the uniqueness theorem is proof for gamma when gamma is lie between 0 to 1. Now then for different values of omega, lambda and gamma, the boundary problem are solved numerically. Table 1 represents the value of f double dash 0 for gamma, omega and lambda. In first part of the table contains when gamma is live, when our omega and lambda is 0, and we compare our results with Cotell's results, and it seems a good agreement, and we are confident enough for further computation. It is also noticed that f double dash 0 is negative when gamma is lie between 0 to 0.5, and f double dash 0 is positive when gamma is lie between 0.5 to 1. It is also noticed that when omega is increasing, the values of f double dash 0, the absolute value of f double dash 0 increasing, but opposite scenario has been seen when, and that time the values of absolute value of f double dash 0 decreasing. For validation of our new existing invention results, we plot f double dash 0 with respect to lambda and omega for gamma equal to 0.3 and 0.7. In both cases, it is observed that f double dash has a unique value. It is also worth mentioning that in figure A, it is noticed that for large value of lambda, the flow domain does not remarkably affect for permeability parameter omega. In figure 3, in all the pictures, the velocity profiles are plotted for the velocity ratio parameter gamma equal to 0.3, and it is observed that all the velocities are decreasing for increasing our parameter values omega, lambda, and in this case omega. And in figure 4 is plotted, velocity profiles are plotted in figure 4 for the ratio gamma equal to 0.7, and in all of the cases it is noticed that our velocity increases for increasing both the parameter values lambda and in this case omega. So summary of our work: the following significant outcome may be summarized based on present analysis. We first prove that the solution exists for our resulting nonlinear singular nonlinear boundary problem. We also observe that when plate velocity is greater than free stream velocity, then both the velocity profiles are decreases for increasing our slip parameters or porous medium parameter. Again, when plate velocity is less than free stream velocity, both the velocity profiles increases with increasing slip and permeability parameter. And we found an exact solutions when our plate velocity UW is equal to free stream velocity. And it is noticed that when lambda is large, that is larger value of slip parameter, the permeability parameter omega does not affect remarkably on the flow domain. And that is all, and this is my references. And is there any question?